Maybe it's not so obvious, but water is absolutely essential to space travel. That's not just because it's crucial for all forms of life. Without water, you'd die in just a few days. But it also contains the two fundamental chemical elements needed to refuel our rockets, service machinery, and allow astronauts to breathe. With so much talk about the moon being used as a potential stepping stone on the way to Mars, lunar ice is exactly the reason why. Scientists have known the moon may harbour frozen water in the cold depths of its polar craters since the 60s, yet it wasn't until a decade ago that this was 100% confirmed, and now the US, Europe, and China are all investigating ways to rob the moon of its precious resource. Why is there water on the moon? How did it get there? And is there a way we can harvest it in the future? The moon has virtually no atmosphere. It ends barely a millimeter above its surface, which is relentlessly bombarded by solar wind and radiation every day. Wherever the sun's glare touches, any liquid or solid water is evaporated and lost to space, because the moon just does not have the ability to trap water vapor like our home planet does. Don't feel too bad though, because every part of the moon enjoys some shade, some areas more than others. Our lunar friend is angled in relation to its orbital plane in such a way that in some deep craters near the moon's poles, the sun never shines. In these freezing depths, water stays frozen, essentially clinging to the moon's surface. Researchers at Caltech were the first to suggest this possibility in 1961, and since then, a growing body of research into lunar water has been compiled over the course of numerous space missions, and an awful lot of complicated maths and science. In 1994, the US Clementine spacecraft suggested potential ice in the moon's poles, followed by NASA's Lunar Prospector in 1998, whose neutron spectrometer confirmed that some lunar craters were rich in hydrogen, probably in the form of water or hydroxyl, 300 million metric tons of it, according to one calculation, with higher estimates forecasting as much as 1 billion tons. At the end of the flight, NASA crashed the craft into one of the moon's craters. They were looking to see if a plume of water vapor was ejected by the collision. Unfortunately, they saw nothing. Despite America's efforts, it was India who were the first to definitively confirm the presence of water on the moon. When their Chandrayaan-1 spacecraft launched the moon in 2008, distinct signatures were recorded from the lunar surface confirming that there is indeed ice up there. Chandrayaan released the Moon Impact Probe, which touched down at Shackleton Crater, further verifying the discovery. On board, the mission was NASA's Moon Mineralogy Mapper, or M3 for short, which scanned the upper layers of the moon's regolith by beaming light and radio waves at the moon, then recording the signature of the spectrum echoed back. Using this method of detection, they were able to take a dive into the chemical composition of the moon dust from a distance, confirming that there were chemical bonds between some hydrogen and oxygen molecules on the moon. The next year, NASA took another shot at crashing a spacecraft into a similar crater. Though they had some trouble detecting the plume visually, this time they had success recording spectral evidence of the plume's chemical composition. By measuring ultraviolet and infrared radiation bounced off the expulsion, the dust cloud contained somewhere around 5% water. Promising results. Since these tests were all performed on the upper layer of the moon's regolith, it is possible that the ice extends even further down where we have not detected, and where temperatures are even lower. Ergo, there may be sizable tracts of preserved H2O, or its more reactive cousin, OH, underneath the visible crust. For some, this discovery may be great news, and for others, it's unreconcilable with common logic. The moon is a rocky, celestial object. Its surface is covered in fine, dry powder. It doesn't resemble Earth in the slightest. Water molecules are probably the last compound you'd expect to find in such a barren, uninviting landscape. But water is on the moon, and although it may not be at the right party, we do have a few guesses as to who its ride was. There are a number of possibilities. One suggests water-laden asteroids which collided with the moon in its history deposited icy fragments, and some of them have been preserved at the moon's poles. After a long history of being bombarded by foreign visitors, the moon has racked up some considerable stocks of water. In the same way that small celestial bodies like comets may have brought water to the moon, they can take it away too. In 2019, a group of researchers from the Johns Hopkins University Applied Physics Laboratory found that streams of meteoroids colliding with the moon knock ice from the surface, vaporizing it, when it is then stripped away from the moon and lost to space. According to Richard Elphick, a scientist at the NASA Lunar Atmosphere and Dust Environment Explorer project, the moon doesn't have significant amounts of H2O or OH in its atmosphere most of the time. But when the moon passed through one of these meteoroid streams, enough vapor was ejected for us to detect it. And then, when the event was over, the H2O or OH went away. As well as watching celestial pyres from outer space rid the moon of its water, NASA have also been investigating the endogenic theory for how water appeared on the moon, and evidently it may be a slow, continuous process. We've talked about how the moon is subject to the glare of our star, the sun, and so when positively charged hydron atoms from the solar wind reach the moon and strike the surface dust in the right way and at the right speed, about 1/3 light speed, they break oxygen bonds in the lunar dust. Moon dust is composed of roughly 45% oxygen, and when these molecules are detached, they can combine with the hydrogen atoms to form either water or hydroxyl. Though it appears to happen on an extremely small scale, the collisions accumulate over massive periods of time, eventually leading to a growth in H2O deposits, most concentrated in the polar craters of the moon, where the sun never shines, where the ice isn't stripped away from the moon. And so, it seems, the moon is growing its own ice. The confirmation of water's presence on the moon is really good news for the future of space habitation, especially with NASA pledging to return to the moon by 2024. The two elements of water, hydrogen and oxygen, are essential for refueling a rocket. While hydrogen is used in the fuel itself, liquid oxygen, or LOX, is needed to keep the combustion going. Carrying large volumes of fuel into space is extremely expensive and impractical, especially on long-haul missions like traveling to Mars. Let's say that we establish a future moon base, and its job, among research and co., is to harvest lunar water. By splitting this water into its constituent parts, we have a reliable and much more cost-efficient source of rocket fuel. This possibility is more profound than it sounds. It means the moon could act as a stepping stone between Earth and Mars, and other distant trips into space. The fact that a rocky body like the moon can hold water in its crevices also brings hope that similar planets or moons can be used to refuel rockets hundreds of years in the future, when we, fingers crossed, venture beyond the confines of our own solar system. To open up enticing opportunities for deep space exploration, NASA envisions harvesting the moon's H2O resources and transporting the water to holding depots on the moon or in Earth orbit, where rocket modules can dock, refuel with the extracted hydrogen and LOX, and continue to their destinations. For the moment, it seems we have all the technology and engineering to extract water from the moon in almost any form. The challenge is deciphering which method to use. Until we have certain results about where the water is distributed and what form it is in, it will be difficult to design the perfect extraction equipment. Gathering water from the moon's icy regolith is sure to be a difficult process, and there are multiple ways you could go about it. One method, thermal extraction, aims to sublimate the ice bed into water vapor, which can be trapped, refrozen, and sent to chemical processors. Unfortunately, this isn't the most energy efficient, since a lot of energy is lost to the surrounding heat instead of the ice we want to warm. The miner's approach suggests mechanically cutting the ice out of the moon's rock and hauling it to a holding base, but many have said this method is rudimentary and awfully cost inefficient. A recent report from the University of Central Florida earlier this year has suggested a simpler and more cost-efficient process dubbed Aqua Fractorium. It is dependent on ice being just as hard as almost any other kind of lunar rock in permanently shadowed regions of the moon. Constant asteroid bombardment in the moon's history has reduced these rocks and ice to fine powders, which can be easily drawn up into a filter to separate the finer grains of ice from the heavier rock powder. Philip Metzger's valuable research into the potential of Aqua Fractorium has earned him a grant to investigate the concept further. It may be that this is our most viable option for harvesting lunar water, and University of Central Florida researchers have suggested that it is not only less complex than phase change extraction, but staggeringly more energy efficient. Even more importantly, the filtration units could be used to separate and store alternative useful materials, like rare metals crucial for modern electronics and helium-3, a potential nuclear energy source. That's good news for the environmentalists because, in Metzger's words, I believe that by the end of the century we can move more than half of the mining machinery off the planet, which would be extremely beneficial for biodiversity. Yet another technique which aims for cost efficiency was put forward by George Sowers at the Colorado School of Mines, who suggests using a large concave mirror to reflect solar radiation into the moon's polar craters, subliming lunar ice which then condenses on a tent cover, ready for collection in nearby tanks. Some observant viewers may see how this resembles the mechanic used in those emergency solar stills included on board almost all emergency rafts, harnessing the infrared radiation from the sun to evaporate and thereby desalinate ocean water. Of course, there are some looming problems and challenges that need to be overcome before we can start thinking seriously about setting up this equipment on the moon, so don't expect to be drinking space water anytime soon. One is that we don't yet have perfect filtration membranes to separate lunar ice from dust, which pretty much undermines the entire Aqua Fractorium operation. We have some membranes that function on Earth, but more work needs to be done on lunar dust samples before we have a working product. Until we do sufficient on-site testing, we also won't know how stable ice extraction equipment will actually be in operation. They may need routine maintenance by astronauts. This could work at a lunar base, but generally the lower the maintenance necessity and safer the infrastructure is, the better. We also need more information on what factors go into running these machines at the lunar poles, because protecting extraction equipment from the extreme cold is in a very different league from temperature shielding today's rovers and prospectors. A reliable and cost-efficient supply of water which can be electrolyzed into rocket fuel and useful materials and minerals could be the key to establishing a lasting lunar base, or, as the European Space Agency imagines it, a moon village. Despite some notable setbacks, like the loss of India's Vikram lunar lander last August, we are on good track to compiling a map of where the moon's water assets are located and how we can glean them. That is the joy of science futurism. We know we're far from achieving our goals right now, but with a growing knowledge of what steps we need to take to get there, we can make hopeful progress to almost any practical future. And lunar mining is very possible, says Metzger, as long as we keep making these crucial, incremental advances towards it. Videos like this would be very difficult without your support. If you'd like to help me continue simplifying complicated subjects into interesting videos and see all new videos 3 weeks early, you can do so at patreon.com/26D. If you want to learn more about lunar water and moon mining, I've included a list of sources in the description of this video. And please, if you enjoyed this video, you can be notified when I upload more by subscribing below. Thank you for watching.